Okay, good morning, blah, blah, blah. Okay, let's start. Oxygen molecule. So this molecule is made out of two atoms, which makes it a diatomic gas. If it's in the gas form lah. Two atom, diatomic gas. Sebab dia dua, dalam satu molekul dia dua. Dia kena exist as two, as a pair. For example, kalau krypton, Kr ke? Krypton can exist as a single atom and can make up the gas. So this is also called the krypton molecule or the krypton atom. Okay, so this is just one atom and we call this monatomic gas if it exists in gas form. Okay, so the mass of a krypton, contoh alah kita Google lah. When I use contoh mesti jadi salah. So let's Google what is the mass of the atom. Mass of, oh I think it's in the book. Page. Skip. Okay, molar mass of krypton, molecule mass. So the molecule mass of a krypton is 1.3915 times 10 to the minus 22 gram. This is per molecule and its molar mass. Ya, kita buat pasal krypton dulu lah. Untuk yang dah faham benda ni, bear with me as I try to make your friends understand juga. Kita nak berjaya sama-sama. Okay, so this is the mass of a molecule. So di dalam gram This is mass of molecule. So ataupun mass of atom lah. Mass of krypton atom. Okay, so this is 1.3915 times 10 to the minus 22 grams. If I wanted to say what is the molar mass of the krypton atom. So molar mass, nama dia molar, molar. It's the mass of 1 mole. It means the mass of 1 mole. Okay, so what is the number of molecules in 1 mole? 1 mole has 6.023 times 10 to the 23 atoms. That's your Avogadro constant, right? Which is also your Na. How do we find the molar mass? It means that we need to know what is the mass of 1 mole, right? Mass of 1 mole. I have the mass per atom. I want to know what is the mass of 1 mole. So if I know the mass of 1 atom, so I'm just gonna kenapa sharing is paused? Can you guys see this screen?
Yes, doctor.
Yes, doctor.
Yes, doctor.
Okay. Sebab dia tulis sharing is paused. Okay, that's good. Nasib baik tak. Which means that now I have to multiply this with the Na or the Avogadro constant. Okay, Na, which is this amount. Okay, this is 1 gram, sorry, this is something gram over atom, right? When I multiply it with the Na, I get atoms. What is the number here? 6.023 times 10 to the 23. Number of atoms per mole. So now what do I get? I can cancel out atom with atom. So now I am getting mass per mole, which is mass of 1 mole. So this is your capital M, your molar mass. Okay?
Doktor,
Yep.
tak bergerak.
Tak tahu apa yang doktor tulis tadi.
Ha.
Nampak tak?
Baru nampak.
Okay. Okay, so I'm going to repeat this part lah. So the mass of 1 atom of krypton is gram per atom. When you times it with the Na, which is your Avogadro constant, you get 6.023 times 10 to 23 atoms per mole because it gives you the number of atoms per mole. And then crossing out atom with atom, you get grams per mole, which is mass per mole. Grams over mole is the mass for 1 mole. Okay, so that is your capital M. So where is your small m? Your small m is this guy. This is your small m. When your small m times with Na, you get capital M. Okay, so they are different by the Avogadro constant lah. So if I had the molar mass and I wanted to know what is the mass per atom or what is the mass per molecule, I would just need to divide the molar mass with Na to get my small m. Okay, is that clear for everyone? Okay tak? Faham tak?
Faham, Doktor.
Okay, that's good. Okay, kalau ada soalan tanya don't be shy. Okay, moving on. Let's do a little recap on what we have learned so far because we have learned a lot. This chapter is just like panjang gila and orang saja bagi saya suffer kasih saya chapter ni. Video dia susah kot nak buat. Okay, where are we? Jangan cakap kat dia orang pula. Jangan cakap kat lecturer lain. Dia kena gaduh pula. Okay. Kita dah sampai sini dah. Have we done this one? Yes, we have. We have learned this one as well. Oh my god, banyak gila. This one dah. And this one. Okay, we stopped here, but actually I showed you about work done using my video on YouTube. But let's do a recap from here, starting here. New slide. Okay. What have we learned so far? So the first subtopic we learned about ideal gas. I'm sorry, I'm just going to repeat myself over and over again because there's a lot. Okay, so PV equals to nRT. We know this already. If something is constant, move it to the other side. So you get P1V1, P2V2, P1 over T1, P2 over T2, etc. You know this, okay? And then we have the KE, which confused you guys still a little bit, but hopefully now it's cleared up. So KE is 1 over 2 mv squared average squared equals to 3 over 2 KT. And we have learned about the degrees of freedom, which means that we can generalize this equation to become F. Okay, and the degrees of freedom is 3 for mono, 5 for di, and 7 for poly. Okay, kita dah belajar pasal ni. So we know that the degrees of freedom affects the KE. So it should be affecting a lot of other equations too in chapter 15. So the next equation that we learned was the VRMS, which is obviously going to be affected as well. And this is 3 over 2 KT F over 2, sorry, it's FKT over small m or FRT over big M. Okay, if you're not familiar with the F equation, just use 3 KT over M, then substitute the number with the right number lah. 3 for mono, 5 for di, 7 for poly. I just remember the 3 KT over M. I'm not used to the F, but it's up to you. Which one is more comfortable to you? You memorize that and then adjust accordingly. And then we learned about VRMS, and then we learned about, what was it? Apa kita belajar lepas tu? Lepas KE, kita belajar work done, right? We learned about work done. We learned about work environment. If the environment loses energy, it actually goes to the gas system. Or if the gas system is doing work done by gas, so work done by gas, it means that the gas is losing energy and this energy goes to the environment. Okay, mesti macam confused kat sini kan. Okay, so if I say positive W, if I say positive W, it means work done on the gas. And work done on the gas means compression means we compress the gas. It means negative change in volume. Okay, positive work done on gas means we compress the gas, negative change in volume. And this also means that the environment is losing energy. When we are doing negative work, the work done is by gas. By gas. Tadi on, this is on. Now it's by. So now it's expanding. Alah, tak nampak. Expanding, and the change in volume should be positive. If the gas is losing work energy, that means the work energy goes to the environment. Okay, memang energy cannot be destroyed, right? So it has to go somewhere. If my gas system is losing energy, it goes to the environment. If the environment is losing energy, it goes to the gas system. Memang takkan pergi mana-mana lah. Kita assume this is the ideal case. There's no air resistance, there's no whatever lah, tak ada benda lain. Kita cakap for ideal cases. So this simplifies things. Okay, so that is work, compress and expand. And then we talked about CV, right? CV, CP. CV, CP. Let's use a different color for that. New slide. Okay, so we talked about the molar specific heat capacity. No, there's no capacity. It's molar specific heat for gas. Okay, specific heat capacity was for chapter 14. It was C. This one is CV, CP. It's molar specific heat. Hari tu specific heat capacity. This is molar specific heat. Okay, so we have two types, which is the CV and also the CP. And we know that CP should be greater than CV because it is actually CV plus R. CV pula, the values for mono is 3/2R. For di, it is 5/2R. And for poly, it's 7/2R. Let's just focus to di only. If I wanted to know what is my CP, I can just substitute this guy, 3/2R for mono cases plus 2/2R. This gives me 5/2R. So CP will always be plus 2/2R, always. So this is for mono. Okay, you can do the same thing for diatomic gases as well. When do we use CV? When do we use CP? We use it to calculate for Q that is at constant volume. What is the process name of constant volume? Have we learned about that? Don't think so. Belum lagi kot. Q at constant volume, we use CV. Nanti kita akan belajar bila betul-betul nak pakai ni. So that is it's N CV delta T. Okay, and then this guy is used at Q at constant pressure. That is N CP delta T. And there's another equation that we learned from this subtopic, which is delta U is actually N CV delta T always. Always, So this is another equation for delta U apart from NR delta T and apart from Q plus W. Okay, so what is CV? CV is this guy, depending on the type of gas. Okay, I think that was it. Let's continue. Kita akan masuk thermal processes in gas. Oh, kita dapat ni lagi. Okay, let's do this one. Determine the work done to compress a gas contained in a cylinder from 80 centimeter cube to 40 centimeter cube with a constant pressure of 1.2 times 10 to the 5 Pascal. Okay, so the pressure is given. Saya nak belajar menulis dengan cantik-cantik sikit. Pressure is 1.2 times 10 to the 5 Pascal. And we have the change in volume, right? This is centimeter cube. So we know that this is volume. So our volume, the change in volume is from 80 to 40. 40 is the final, 80 is the initial. So 40 centimeter cube minus 80 centimeter cube will give me minus 40 centimeter cube. Betul tak? Okay. And then this guy is not in the SI unit, so I need to convert that. So times with 100, sorry, it's 1 meter. I want to convert to meter, so my meter should be up on the top. 1 meter, I want meter, so it goes on the top. I want to get rid of my centimeter, so 100 centimeter. But this only cancels out 1, so I need 3 of these. So cube lah. Okay, so I have centimeter cube, which cancels out, and then this is minus 40 divided by 100 times 100 times 100 meter cube. Okay, tak tahulah berapa tu, banyak dia punya zeros. So it's asking determine the work done with a constant pressure. So work done, we know the equation is W equals to minus P delta V. So P is 1 minus 1.2 times 10 to the 5. And my change in volume is a minus 40 over 100 times 100 times 100 meter cube. It says PA. Okay, so if I were to use my calculator, because I'm feeling rajin hari ni, 1.2 times 10 to the 5, okay, times 40 divided by 100, divided by 100, divided by 100. Hopefully dapat jawapan yang sama dengan belakang. So that is 4.8. What is the unit for work done? It is type of energy. Everything that is in the first law of thermodynamics is in joules. So it should be in joules. The negative is cancelled out with this negative, gives me a positive work done. What does it mean when I have positive work, guys? What does it mean?
Work done on the system.
Work done on the system, correct. Work is done on the system. On system. Okay, so let's see, harap ni betul lah. Yay, betul. Okay, so that is how you use the equation. Keep moving on. Next one. A gas system with an initial volume of 2 meter cube. So this is our V initial, 2 meter cube. Is compressed. So work kat sini compressed. So kita tahu macam, okay, maybe it's a positive work. With a constant pressure, V is 25 kPa, kilopar, bukan kPa, kilopar, kilopascal, or 25 times 10 to the 3 Pascal. Determine the final volume of the gas. So it's asking what is V final? If the work done on it is 5 kilojoules. So selalunya dia akan cakap work done is 5, work done is 3, work done is blah blah blah. They don't tell you whether it's positive or negative. So you have to look on it. They say work done on, so that should be a positive, and the word compress should be work done positive. Okay, so now we go with our equation. W equals to minus P delta V. Our P is 25 times 10 to the 3 times with V final minus V initial, which is 2. Okay, and we know that the work done is 5 kilojoules, so 5 times 10 to the 3. So kena buat lah. So that is 25 times 10 to the, buat je lah. V final minus plus 25. So that is a 50 times 10 to the 3. Okay, so this is 5 times 10 to the 3. Okay, malas ni. Okay, 5 times 10 to the 3 minus 50 times 10 to the 3 divided by minus 25 times 10 to the 3. Okay, so that will give me V final as 22.5 meter cube. Should be compressed. Okay, ni salah. Saya salah kira. What am I missing here? 5K to 25 kilopa, betul. V final minus 2. So if it is compressed, the V final should be smaller than the initial volume. What's going on here? Okay, I'm going to try again. 5 times 10 to the 3. Final minus 2, 20, 50. Okay, 50 times 10 to the 3. 5 times 10 to the 3 minus this answer divided by 25 times 10 to the 3. Okay, dapat minus 1.8. What happened just now? So minus, sorry, it should be positive. 1.8. Alamak, tertinggal minus. Oh yes, tertinggal minus. 1.8 meter cube. Okay, so just now I got 22.5, I think. And immediately I know, okay, I did something wrong here because when we are compressing the gas, the final volume should be smaller. So when I looked at my answer, okay, it immediately tells me that I'm doing something wrong. So you should use that to check on your answer. So always use your logic. So this is 1.8, definitely smaller than 2. So let's see. Yay, so that is the answer. Okay, moving on. If you have any questions, feel free to interrupt. Okay, next one. A sample of gas is heated at constant pressure. So P equals to 1 times 10 to the 5 Pascal. This leads to an increase in volume. So we know that the volume is expanding. So delta V is positive from 2 to 5. So delta V is 5 minus 2 meter cube. Find the amount of work done by the gas. It's asking you by the gas in this expansion process. So ada 3 hint kat sini. Increase, expansion by the gas. So we know that work should be negative. Okay, dia kasih hint siap-siap. So W work done equals to minus P delta V. Okay, so work done ni sebenarnya senang je. You just have to get the right equation. Make sure you have the negative sign. And then this is 5 minus 2 is 3 meter cube. So that is 3 times 10 to the 5 joules. Negative. Tertinggal negative. Okay, so see. Yes, the sign is negative. So the work is done by the gas. Correct. Okay. Oh, banyaknya. Soalan. Sekejap. Bila kita nak start belajar Isobaric semua ni? Okay, sekejap. Okay, lambat lagi. Alright. Tak apa, kita teruskan. Okay, this one. Sebelum tu dah kan? Okay. So an ideal gas absorbs 1000 joule of heat. Kat sini cakap absorb of heat. So Q should be positive 1000 joules. Okay. As it expands, expand. So you know that delta V is positive. This is expansion. Expansion is usually negative work. Okay. From its initial volume of 1, so V initial is 1 times 10 to the minus 3 meter cube to a final volume of 2 times 10 to the minus 3 meter cube. Under a constant pressure, P equals to 2 times 10 to the 4 Pascal. What is the change in internal energy of the gas? So now we are talking about first law of thermodynamics. It's asking you what is U. We know that the equation for U is delta U is Q plus W. We have Q, but we don't have W, so we need to calculate for that using these values. So W is equal to minus P delta V minus 2 times 10 to the 4. Delta V is, or everything is in SI unit, so that's good. 2 times 10 to the minus 3, so 2 minus 1, so it's just 1 times 10 to the minus 3. So this gives me a negative work of minus 20. Yeah, 20 joules. So if my Q is positive, it is absorbing Q, but at the same time, it is doing work, which means that if I have a syringe, it is being, the environment is giving it Q, but at the same time, it is expanding. This is not a syringe, but it is expanding. The volume is expanding as it absorbs the Q. Okay, so 1000 minus 20. Hopefully this is right. 2 times 10 to the 4 times 1 times 10 to the minus 3. Betul, good. Okay, so this is 980 joules of change in internal energy. Betul. Okay, so work done, mula dia kira work done, which is how we did it. And then we used the first law of thermodynamics. This is the change in internal energy experienced by the gas in the system. Okay, dia absorb lebih banyak daripada dia buat work. So, banyaklah energy dia dalam tu. Okay, moving on to the next one. Okay, 1 mole of ideal gas, what time is it? 1 mole of ideal gas is initially at a temperature of Ti 0 degrees Celsius. So this is not in Kelvin, so let's change it. 0 degrees Celsius, change it to Kelvin, 273 K. Undergoes an expansion. Yay, we have the hint over here. So that means our work should be negative. Okay, let's just write it here. Negative work, possibly. At a constant pressure of 1 atm. So P is 1 atm. Convert that to Pascal, 1.012, good. Times 10 to the 5 Pascal. And it expands 4 times to its original volume. Okay. How do we calculate for the V? Anyone wants to try? How do we calculate the V?
Equal to 4V, lepas nanti cancel.
Equal to 4V, nanti cancel. Equal to 4V, nanti cancel. Cancel macam mana tu?
Nah, kita tak tahu nilai V tu kan. So nanti dalam calculation tu kita just ambil value 4 je. V tu kita cancel out.
V tu kita cancel out. Okay. Okay, I think we should do this together. Okay, I'm gonna give you guys 7 minutes to try. I'm gonna call out someone to do A and someone to do B. Okay, soalan ni macam mencabar sikit kan, baru seronok nak buat. Okay, please try. Let's come back at 11:45 and let's discuss. If you get it wrong, that's fine. You are here to learn. PM pula dah, mampus. AM. Oh, sorry, saya tak cakap mampus. Okay, let's come back at 11:45 AM. Let's discuss. It's okay if you get it wrong. Just try, okay? Ini tak tahu tau, okay? Just try first. Excuse me. Okay, 2 more minutes. Do we have any volunteers? Hihihi, tak ada.
Doctor, can we know the final answer?
Final answer. Sekejap. Nanti saya kena tengok solution. Saya pun tak tahu. Sekejap. Tak nampak. Stop share sekejap. Kejap ni. So the answer is 1092K Kelvin
For B,
minus 6.81 kilojoule. minus 6.81 kilojoule and 102 K. Okay, let me write that down. Share screen. Okay, did anyone manage to get the answer? Kalau ada boleh share. Sekejap Jawapan A is 1092 Kelvin and B is minus 6.81 kilojoules. Okay. Ada tak siapa-siapa yang dapat jawapan ni? Just A. Ada tak dapat A? No one? No one got it?
Dapat A.
Dapat A. Siapa tadi? Fakri
Dapat.
Okay. What did
Fakri,
you...
Fakri.
Alright. What did you do? So A.
V1 over T1
Mm-hmm.
equal to V2 over T2.
Okay. So V1 is
So V2 is sorry. So T2 times 4.
V22 times 4. Macam mana?
Can V1 equal to 4V kan? So nak dapatkan
V.
right, so can the multiple of 4, then the value of T2 is equal to 4T1.
The value of T2 is equal to 4T1.
Yes.
Oh, okay. Okay, betul. Ni shortcut lah. Okay, saya cerita macam mana. So V1 is just V1 and they said they expand to 4 times its initial volume. So actually V2 is 4 V1. So betul lah apa yang Fakri buat tu, tapi Fakri terus skip to 41, right? So V1 is 4 V1 where let me try again. V1 is just V1. V2 is 4 V1 sebab V2 expanded to 4 times of V1. So bila kita nak masuk dalam equation, it becomes V1 over T1 which is 273 and V2 is 4 V1 over T2. V1 cancels out and we have T2 as 273 times 4 which is right apa yang Fakri buat tu. Okay, so dapatlah 1092. Okay, did anyone get the part B? Part B senang je kan? Should be. Anyone wants to try part B? No one? Okay, saya panggil can I get Louis? Tak pernah panggil Louis.
Yes, teacher.
Hi, can you do part B? Have you managed to do it?
Yeah.
Okay, so what is the work done? How did you do it?
I use PV equals NRT to find the volume.
PV equals to nRT to find the volume.
Yeah.
Okay, so macam mana tu?
And I got the volume is 0.02243 and
0.0224 meter cube.
yeah. And then I use work equals negative P delta volume.
Macam mana?
I use work done equals to negative P delta volume.
Oh, you found out negative V delta. Oh, is it this one?
Yeah.
Okay, saya tak dengar. Okay, lepas tu?
And the difference of volume is 3V.
Okay, it's 3V lah sebab V final minus V initial. Okay, so P is 1 1.012 times 10 to the 5 Pascal. And Louis said because the V final is 4V1 minus V1, it should be 3V1. Betul tak, Louis? Is that how you did it?
Yes.
Okay, so and she already calculated for V1, which is this guy. So she substituted into this equation. Okay, betul, betul. That's one of it. That's one of the ways to do it. So 3 times 0.0224. Okay, so that will give you negative work done, which is betul lah because it is expanding. Is there another way to do this? Padam ya. Is there another way to do this? No? No other way? Okay. Sekejap, let me think. Ada tak? V final initial. Tak ada kot. So this is, okay. Is anyone confused why kita cari V1 kat sini and then this equation? Is anyone confused by part B? You need to let me know so I can repeat myself. Is everyone okay with this part? It's okay if you don't understand. You can tell me. So no questions? Is everyone okay? Everyone comfortable with this question? No answers? Everyone's scared?
Okay.
Okay. Umar je yang okay. Orang lain macam mana?
Okay, doktor, okay.
InsyaAllah.
Okay, doctor. Okay, that's good. Okay, moving on. Okay, so this is how they did it for V1 over V1. Okay, sama je lah macam kita buat. And this one, 3 W equals to minus 3 and okay, so basically they use PV equals to nRT and substituted into this equation. Because they got P, they got this guy as 3 PVI minus 3 PVI again. So this is, the delta is already gone. So they said, okay, we can substitute minus 3 nRT over here, which is the same as what Louis did. Sama je. What Louis did was she solved for PV equals to nRT and then use it into the equation W equals to minus P delta V. This person, they used the W equals to minus P delta V, solve for that, got rid of the delta, which means that the PV is now equals to nRT lah. But this guy ada kat situ lagi, so just let it be there. It's just a constant there. So this guy is substituted with nRT. Sama je. Boleh juga macam tu. Both steps are correct. Choose the one that you are comfortable with. Okay.
Doktor,
Yep. Yes. Muted.
kenapa, sorry. Kenapa T tu kita tak substitute dengan 1092?
Kenapa kita tak substitute T tu dengan 1092? Oh, okay.
Ya.
PV equals nRT. Okay, if I wanted to use the final, betul-betul. The question is confusing. There's another way to do this, which is minus nR delta T. In this case, you have the T final and the T initial. But in this case, this is the VI, the V initial. Okay. Here they use the V initial, which means that whatever goes into the equation should be T initial as well. Patutnya dia label lah. T initial. If this was V final minus V final, contohlah soalan tu dia kasih kita V final instead of V initial, right? So this would be the T final. Okay, but because we used in reference to VI, everything should be in the initial state. So this is TI. There's another way to do this, which is minus nR delta T. Should we try it? We should. Okay, let's try. -1 8.314. What is delta? Do we have the final? Yes, we do. Final is 1092. So delta T is 1092 minus 273. Let's see. That is 819. Okay. 819 times 8.314. Give me 6809 joules. Sama tak? Sama. Sama je. Okay. Is that confusing or is that okay?
Okay.
Okay. Anyone still confused? This is the third approach. Second approach. Louis' method was the first approach. There's a lot of ways to do this. Okay. So again, I'm going to repeat myself about the initial and final. Here, we use delta V in reference to V initial. So it was V, this was our V final, this was our V initial. V final, we said it was 4 VI, so minus VI. So we got 3 VI over here. And then it became 3 PVI. Oops. It became 3 PVI. Over here, minus 3 PVI. We know that PV is equal to nRT. If this guy is in VI, this guy should be in VI, TI as well. So now I substitute 3 nRTI. Okay, so this is where you need to decide. I mean, this is how you know that you need to use the initial temperature. Okay, whereas if you wanted to use, you know that PV is equal to nRT. If I have a delta over here, I need to balance it out by having a delta over here. I know that N cannot have delta, R cannot have delta for sure. So it only leaves me with T having the delta. So P delta V is equal to NR delta T. Substitute that into the equation. N is 1 mole, R is just your constant, and delta T, you got this from the T final minus T initial, which is 819. Okay, so I hope that's clear. You can use whichever solution that you are comfortable with, okay? Moving on. Okay, so the results of delta U, what time is it? Okay, let's take a 5-minute break. We will come back to discuss about the 4 thermal processes in gas, okay? I think that's pretty enjoyable. So 5 minutes. If you need to go to the toilet, etc.
Can I go eat then?
You can eat what? You want to go eat?
Yeah.
You can eat in front of the laptop, but suka hati lah. I don't mind. Five minutes means 12:03. 12:03. 12:03. Come back. PV thermal processes. Excuse me. Okay, I hope you guys are back. Let's continue. Okay, so I'm going to continue with the results of delta U in terms of a PV diagram. Okay, so the changes in the internal energy result in the change of state, that is changes in measurable, blah, blah, blah. Okay, so basically it's saying if you have a change in delta U, it will be affecting either P, T, or V. That is what it means. So these changes can be shown in terms of a graph. And we call this graph as the PV diagram. It looks like this. P, they say, whoa, it's funky. Okay, so V is here, volume in meter cube, and P is in Pascal. Okay, don't write P. Pressure is in Pascal. Okay, and you have learned to do these graphs in your lab, so that's great. Let's move on to what are the changes that we can see. So here is a type of, sorry, this is the PV diagram for an isothermal process. Kita akan belajar isothermal ni apa. So isothermal, because iso means same, thermal is temperature. So it means that the change in temperature is 0. So if the change in temperature is 0, which means that along the curve, the T is constant. So if this, sorry, T is constant, but this guy for a graph that is higher in position compared to this guy, we can say that this graph A, B has a higher temperature than the graph A prime, B prime. Contoh lah. So the difference is shown by the position of the curve. Dia tunjuk the change in, bukan the change, the difference in temperature, because this is not the change. This is one process, this is one process. Process 1 has 22 degrees Celsius temperature constant. Process 2 has temperature of 40 degrees Celsius constant. So the difference in the position in the PV diagram shows that they have different temperatures. Okay, so that is what I'm trying to say here. Okay, so this, moving on, kita cakap position dia pun akan berubah lah. So we have 4 types of thermal processes. The first one is isobaric. Iso means same. Baric. Bar. Selalunya bar is associated with pressure. This is how you memorize the name. Isobaric, isobar. Bar is pressure. So same pressure. Constant pressure. Isovolumetric, the volume stays constant. This is delta V equals to 0. Iso, same volume. Okay. Isothermal, same temperature. So delta T is 0 or T is constant. And adiabatic means Q is equal to 0. So how does this look like in the PV diagram? So let's draw it. So if I have my PV diagram, this is P and this is V. Do not label P and V. Please use the full word lah. PRE, pressure lah. Tulislah betul-betul jangan tulis P dengan V je. Okay, so if P stays constant, which means that it should be a straight line in the graph. It can either be here, tak kisahlah. Asalkan you know what the pressure is constant, you can draw the graph like that. So this is for an isobaric. The pressure is constant. Pressure constant. Okay, but the V is not constant, so the V expands. Okay, that goes to the next point. If I say this is my initial point, this is my final point, this is how my curve looks like, it's going to the right, it means that my volume is expanding. And that means that negative work done. I am doing negative work. My system is doing negative work. It is losing energy. So how do I calculate for the work done using a PV diagram? Remember, work done is P delta V minus P delta V. Using this diagram, I can actually find out the work done by calculating the area under the graph. So this is this the same as PV? Yes, it is. P delta V. So delta V is given by, this is V final, this is V initial. So this is, let's say 10, and my P is, let's say 5. So minus 5 and V final minus V initial, that is 10. Ni 10. Dia punya difference is 10. Difference is 10. This gives me a minus 15. Now, what using the same shape, what if my graph started from here to here? From here, let's use a different color. From this is my V initial, this is my V final. I use the same formula, I just calculate for the area, 5 times 10. But now I have to say that my W is positive because my volume is compressed. And my delta V is actually negative. Okay, so it depends whether I'm expanding or whether I am compressing. Even though I have the same shape, even though the area is the same, I need to know whether it's expanding or compressing. If it is expanding, my gas is doing work. So positive delta V means negative work. If my gas is compressing, negative delta V, which means that I am doing positive work. Okay, so nanti kita akan tengok lagi examples of this graph. Okay. Kita buat kemas-kemas sikit lah. Okay, so isobaric is delta P is 0. Let's put it here. Let's get tempat. Okay, so this is a contoh pasal isobaric. Moving on to isovolumetric. So let's use a different color for that. Let's use green. So isovolumetric, as the name says, its delta V is equal to 0. So it means that my P can change, my temperature can change, but my volume needs to stay the same. So in the PV diagram, this is V and this is P. My P can change, but my V needs to stay constant. So I need to pick a point on the x-axis. Which volume is it constant at? Let's say it's 5 meter cube, right? So the volume is constant at 5 meter cube, but the pressure can increase. So this is how my isovolumetric graph looks like. It's a straight line in the PV diagram. Walaupun dia lengkut-lengkut sikit, but it's supposed to be a straight line, okay? So isobaric, straight horizontal line. Isovolumetric, straight vertical line. So isothermal, kita tengok tadi, it was like this. Okay, so isothermal, the change in temperature is constant. So dia tak reflect dekat y-axis or the v or the x-axis because it's a constant temperature. So P is not constant, V is not constant. So tak adalah straight line kat sini. So it's a curve. Okay, so adiabatic. Yes, ada soalan ke, Redha? Tak ada Okay. So adiabatic, it looks like almost the same as isothermal, but it has a steeper curve. Steeper curve. Lagi condong lah kot. I guess the word is lagi condong, lagi steeper lah. Steeper, okay? So it's steeper than isothermal. Why? Because adiabatic happens quickly. So the changes happen quickly. So adiabatic will have a steeper graph than an isothermal. Walaupun dua-dua ada curve, it's not a straight line, but adiabatic must be steeper than an isothermal. Selalunya macam tu. Okay, so now let's write this in a table to make sense of things. New slide. Insert table. Fine. Okay. So we have the isobaric. Let's write that. Isobaric we have, which is P equals to 0. And then we have, let me use this one. Okay, isovolumetric. Oh, kejap. My son is calling. Kejap. Delta V equals to 0. Now, I'm teaching. Okay, thank you. You're welcome. So isovolumetric delta V is equal to 0. Isothermal delta T is equal to 0. It's adiabatic. Is Q equals to 0. Okay, we have delta U in our equation. We have Q, we have W, and we have the PV diagram. So let's write that down. So PV diagram, we know isobaric senang je, straight line, horizontal. It looks like that. Okay, so this is PV. Isovolumetric, kita dah belajar, straight line, vertical, PV. Isothermal, PV, curve. Adiabatic, slightly steeper curve than the isothermal. Like that. Okay. So your graph can go either to the right or to the left. So right means expansion. Sekejap, tak cukup tempat. PV. Going to the right means expansion, means apa? Negative work. And then we have compress, which means that the volume is increasing. Sorry, this is to the left. Okay. Compress to the left. Compress. Positive work. Okay. This is to the right. This is to the left. Okay, contohnya macam this is to the right. Okay, susah. This is to the left. This is to the right. So boleh, mana-mana pun boleh. It depends on the question. Okay, so delta U for isobaric, we know that this is a constant P. So Q for that is Q equals to NCP delta V. Isovolumetric, NCV delta T. We know that the equation for delta U can either be U equals to Q plus W, delta U equals to NCV delta T, or delta U equals to F over 2 nRT. So isovolumetric, isobaric, the work done, P is, this is their general equation, minus P delta V. So this is still P delta V. Okay, usually isobaric memang pakai work done minus P delta V. But in isovolumetric, the delta V is equal to a 0. So minus P0 gives me 0 work done, which means that my delta U is just equal to Q. Okay, and then isothermal delta T is equal to 0. I have delta T in my delta U equation, which means that my delta U is equal to 0 for an isothermal. For Q goes to 0. Wait, Q is at 0. W is W. No, Q is not 0. It doesn't necessarily mean 0 because Q, I know I said that the equation is NCP delta T, but for isothermal only the change in internal energy is 0, which means that Q is equal to minus W. Okay, so this is a little bit confusing. Take note, this is a little bit confusing because I showed you this equation before. Okay, and then W is just minus Q. Okay, and then adiabatic Q equals to 0, which means that delta U is just W, and Q is 0 here, and W is equal to delta U, or just NCV delta T, or minus P delta V. Okay, did I get that right? Let me see. nRT U minus W. Isothermal nRT. Okay, so there's another equation that we have not learned yet, which is for work done for an isothermal is nRT natural log V final minus V initial. Nanti kita akan belajar. Okay, so in general, because we have learned about delta P equals 0, delta V equals 0, delta T equals 0, Q equals 0, I just wanted to tie everything with a PV diagram and hopefully all the equations as well. So apa yang baru kat sini kita tak belajar lagi is this guy over here. Okay. This is new. What else is new? Lain semua dah belajar rasanya. And then we have learned about the PV diagram. Okay, so moving on. This is the PV diagram for all the thermal processes. What time is it? Okay, oh, sorry about that. I'm getting messages. Okay, so isovolumetric straight line, isobaric straight horizontal line, isothermal, adiabatic is slightly curved. Okay, exactly what we have learned. And then the work done on the gas is actually the area under the curve. How you determine whether it's positive or negative work, it depends on the direction of your arrow. This is compression because the volume is going to the smaller volume, going to smaller V. And if you are going to this bigger V, you are expanding. That means you are doing negative work. Okay, positive work. Okay, so positive work done on the gas, negative work done by the gas. Okay, done by the gas, done on the gas. On means positive work. By means negative work. Okay. And then the work done, it depends on the particular path. Even though, okay, let's say we start at 1 and we finish at 3. This guy also starts at 1, finishes at 3, starts at 1, finishes at 3, starts at 1, finishes at 3. But the area under the curve is different. So that means the work done by these processes are different, even though they start and end at the same point. So the way you can calculate for the area is using modern maths punya scale. This is a triangle. So 1 over 2 times 1 times, sorry, it's not 1, times the length of this guy, which is 2, times the length of this guy, which is 2. That is your triangle. And then this guy is a square, a rectangle, sorry, a rectangle. So that is a 2 times 1. So 2 plus 1, 2 plus 2 is 4. So the area is 4 over here. So buat laju-laju je, because this is like basic. And then over here, we have, oh ni susah sikit lah. We have have a triangle over here, a square over here, a square over here. So 1, this is 1, this is 1, this is 1, 1. So that is 1. This is 1 over 2 times 1 times 2. So that is just 1 as well. So 1, 1, 1, this is 3, this is 4. Even though they started at the same point and ended at the same point, they have different areas. So this is 4 joules of work. The arrow is expanding, which means that my work is -4. This guy, the volume is expanding, my work is -3 joules. This guy, the volume is compressing, which means that my work done should be positive. What is the area here? 1 times 3, 1 times 1. So this is a 4 joules. Okay, sama juga. This is positive work. Okay, so just calculate the area. What if your graph is like this? What if your graph is like this? Do you calculate the entire area under the curve? The answer is no. You only calculate up to the x-axis sahaja. Okay? Only up to that point. Below the x-axis, you don't have to care about it. Okay? Moving on. So that was the PV diagram. Okay, so laju-laju je sebab kita cakap pasal isobaric process. W equals to minus P delta V. The heat input is just Q. So delta U is Q plus W or Q minus P delta V. We can also write it as F over 2 NR delta T or NCV delta T. Because this is just delta U basically. Okay, so ni kita dah tengok equation ni semua kita dah tengok. Okay, isovolumetric change in volume is constant equals to 0, which means that this guy is 0. Heat input is still Q, which means that delta U is equal to Q plus 0. So it's just Q. Okay. Then work done in isothermal process. The T is constant, delta T is 0. W equals to minus P delta V. And then they substituted nRT. And as I told you before, if you have a delta, make sure your right hand side also has a delta. So to put in the delta V over there, they had to cancel it out with another V over here. Okay, I know that PV equals to nRT and P delta V equals to NR delta T. But in this case, they didn't want the change in temperature because temperature is constant. So this delta cannot exist. So what happens is nRT, they said, okay, I want to put in the change in volume. So I have to cancel it out with another volume. This cancels out, right? So boleh lah letak kalau nak. It is the same as if I said, okay, I want to put in 10 into my equation, but it needs to be cancelled out by another 10. Sama je. Cancels out. So it doesn't disrupt the math lah kat situ. Okay, I hope that makes sense. That was math. It's not my area. So I tried my best. So basically they put in the delta V over V, and then delta V can also be dV, which is in integration. So you are basically integrating nRT over V. Okay, you don't have to do it. So the final form is this guy. Minus nRT natural log V2 over V1 or V final over V initial. Okay, heat input is still Q. Even though I told you Q is equal to NCV delta T, but Q is not affected in isothermal. Q can still exist because the Q can still be absorbed even though the temperature is constant. Okay, so this is the part that gets a little bit confusing. So I hope you take note on this. Okay, heat input exists for isothermal even though the temperature is constant. Because, okay, let's talk about it. If I have a cylinder of gas and this cylinder has a piston lagi kan, tak apa, bagi korang faham. Okay, so this is a piston. I should label this as a different color, tak apalah. Okay, so I have fire. I heat this guy up. Okay, so I heat it up. And in order for, so this system absorbs Q, right? I heat it up, so it will get positive Q. Great. But I want to make this an isothermal process. An isothermal process, the T is constant. But if I supply heat, I am actually trying to change the temperature, right? So how do I not make it change in temperature? I have to take this energy that I got from Q, convert it into work. So what happens? This Q gets converted into work. So the piston is pushed upwards. So it is pushed upwards, which means that the Q is converted into W instead of changing the temperature. Okay, so in isothermal, delta U is equal to 0 because when we don't have a change in temperature, the internal energy cannot change. But that does not mean Q is not there. So delta U is equal to Q plus W. If I am absorbing Q, I will be releasing W. If I am getting W, I will be releasing Q. So that is how it works for an isothermal. Absorb Q, gets converted into work. Okay, so the piston moves because the gas is trying to expand. Sebab dia dapat Q kan, tapi tak nak change temperature. So dia expand. When it expands, it does work. Q is converted to work. Okay, so this is the equation that you should use to calculate for the work in isothermal. So isothermal ni special case. Okay, moving on to adiabatic. Adiabatic, the Q is, where is it time? Okay, sikit lagi. Adiabatic is Q equals to constant or Q, delta Q is 0 or just Q equals to 0 lah. Meaning that there is no input, no heat input or output. Okay, tak ada orang kasih duit, tak ada orang ambil duit. So you just, if you have 10 ringgit, 10 ringgit is all you have. Nobody is going to give you money, nobody is going to take your money. So Q equals to 0, change internal energy, so delta U Q plus W, Q becomes a 0, so delta U is just W. Delta U is just W. So W equals to delta U, and then just your normal equation lah. Okay, so delta U, you know that it is NCV delta T, berapa kali cakap dah? F over 2 and RT, delta T. Okay, so sama je. So because delta U is equal to W, so you can use work with this equation. So it's just work is delta U, which is just that. Okay, so during a typical adiabatic expansion, the final temperature is lower than the initial temperature. Therefore, using this equation will give us E minus W, which means that the work is done by the system on the environment. Okay, I need to come up with an example on that. Adiabatic expansion usually happens in your car engine. Your car engine, the piston kan, piston to drive the car. When it expands, the temperature drops. Okay. Alah, ni piston korang lah. So this is not my piston. My piston is beautiful. So this is an ugly one. So it expands when it is doing work. It expands and compresses, expands and compresses. The piston moves. Korang tahu kan, tengok iklan selalu ada gambar piston ni pasal changing your car oil. Okay, when it expands, the temperature drops. Bila dia mengembang, when the volume increases, the T decreases. Okay, the T decreases. So this W is equal to the change in temperature. So temperature drops, maksudnya delta T needs to be negative. Okay, which means that the work done is negative, which is right lah because it is expanding. Temperature drops, negative work done. Okay, that is your adiabatic expansion. If I find a video on it, I will show you. Because isothermal and adiabatic is different in a sense that isothermal constant temperature. So the Q is converted to W, but adiabatic there is a drop in temperature or there is an increase in temperature that is converted into work. Okay, so berbezalah dua tu. Okay, so we have come to the summary of this guy. So isobaric, NCP, NCV. Okay, I think this is okay. We have learned about this. Oh, tinggal exercises. Okay, so I am ending class at this point. If you have questions, you can WhatsApp me, ask the group, or ask your friends. Doesn't matter. You can start on your web assignment as well. We have learned a lot on chapter 15. And if you need help, just come to me or you can ask your friends and discuss. Okay, so take care, stay safe. I'll see you tomorrow, I think. Okay, bye-bye.
Thank you, Doctor.
Welcome.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.
Bye.
Thank you, Doctor. Thank you, Doctor. Thank you, Doctor.
Welcome.